Let's go through an example for looking at the difference of proportions. Let's look at gender differences towards Wall Street executives. We might ask, do the proportion of men and women differ in their perception of Wall Street executives as dishonest? So we're going to collect data, and we create the following table of proportions by gender of the respondent. This is from a random sample of data. This is a real data set. And you can see that there seems to be some kind of difference between males and females in the proportion who think that Wall Street executives are dishonest. So if we label group 1 as females and group 2 as males, then we have a value of p hat 1 equal to 0.73 and p hat 2 equal to 0.6. To put another way, based on a sample of random data, about 73% of women think Wall Street executives are dishonest, whereas about 60% of men think Wall Street executives are dishonest. Our orienting question is this difference in the population, right? Is there a real difference in the population, right? So we're going to use this difference in the sample of data to examine this idea. So let's look at the point estimate for the difference. Our single best guess for the difference of proportions of the population is just the difference in the sample proportions. So in that sample, p hat 1 minus p hat 2 is 0.13. We just take 0.73 and subtract out 0.60. So this just reflects the fact that there is a difference between men and women in their perceptions of Wall Street executives. Women are more likely to think that Wall Street executives are dishonest than men. But this is just a sample of data. It's a random sample of data. And we don't know, we don't actually observe the population. Maybe this is just due to random sampling variability. So what we want to do is we want to test a claim about the population. This is suggestive, but it's not a formal hypothesis test. So we want to conduct a test for the difference in population proportions between men and women. As a preliminary step, we should check the failures and successes. For the sampling distribution of the difference in proportions to be approximately normal, we need to have at least 5 successes and failures for each group. As you know, this is an assumption, but we can kind of assess this by looking at this cross-tabulation. So in terms of counts, we see that all cells are above 5, so we can proceed using the 2 independent samples ZTest. Again, this sort of checking for failures and successes expected is based on this sample of data, but it's an assumption about the population. Or it's rather using the population values. After checking that success-failure condition, we can proceed with our hypothesis test. For steps 1 and 2, we set up our hypotheses and set our significance level alpha. For a 2-sided z-test for 2 independent samples, we're treating these 2 men and women as independent, we have the following hypotheses. The null is that the difference in population proportions equals 0. Men and women don't differ in their views of Wall Street executives being dishonest or not. The alternative is that that difference in the population is not 0. The key point here is that men or women could be greater or less than in terms of their views of Wall Street executives being dishonest or not. We're agnostic about that sort of setup. Then we're going to set alpha to 0.05, and we're going to set a critical value. Since we're conducting a 2-sided z-test, that critical value will be set accordingly. For step 3, we're going to compute the test statistic. Right? The test statistic for the 2 independent sample z-test with a 2-sided alternative is given as follows. You take your difference in sample proportions, you subtract 0 because the null is 0. Right? We're trying to see how different our data is from our null, and then we divide by the standard error, where the standard error is calculated as before. Since we typically don't know P1 and P2, those are the proportions for each group in the population, we're going to use the sample proportions when we calculate the standard error. And we can obtain all of our values from these following 2 tables. These give us the proportions and the counts. So if we call females group 1 and males group 2, then we have these 2 sample sizes. So there are 397 females, 413 males. These are the counts for each group. The proportion for females is 0.73. The proportion for males is 0.60 in the sample, and that difference is 0.13. Then what we can do is we can calculate the standard error using p hat 1 and p hat 2 as estimates for P1 and P2 in the population, and we obtain a standard error of 0.033. That is the expected standard deviation of the sampling distribution for the difference in sample proportions. Again, we're using P1 and P2 to calculate the standard error here. Now we can calculate the test statistic. The test statistic is simply that difference of sample proportions minus 0, because 0 is our null hypothesis, divided by the standard error. And we have the z-test statistic at 3.94. This z-test statistic, it lies on the standard normal distribution. With the z-test statistic of 3.94, you should at this point know, using the normal coverage rule, what you know about the normal coverage rule, that 3.94 is a pretty unlikely value on the standard normal distribution. It's nearly 4 standard deviations above the center of that distribution. So this tells us that under the assumption that the proportions of the population are equal, that is, their difference is 0, it's pretty unlikely that we would have obtained the observed difference in our sample of 0.13. We can formally examine this z-test statistic by comparing the test statistic with a critical value or calculating a p-value using the test statistic. So since we're using a two-sided test, we use the following critical value for making a decision. If our z-test statistic in absolute value is greater than or equal to z alpha divided by 2, we can reject the null that the difference in proportions in the population is 0. With an alpha of 0.05, we have the z-test statistic of 3.94 in absolute value. That's greater than 1.96, so we reject the null of no difference in the proportions in the population. To put another way, yeah, men and women differ in their views of Wall Street executives. We can also take the p-value approach. So to calculate the p-value, we take the probability of obtaining a z-test statistic greater than or equal to the one we obtained in absolute value and multiply by 2. This reflects the fact that we might have a difference that is positive or a difference that is very negative. In our case, the p-value is very close to 0. Here we have the sampling distribution. If the null is true, if the null is in fact 0, if the difference in proportions in the population is 0, this is where the sampling distribution should be located using what we've calculated in terms of the standard error. Our test statistic is quite positive, right? And the probability of obtaining a test statistic as or more extreme than the one we obtained is pretty close to 0, so we can reject the null based on that p-value that's pretty close to 0. At this point, we can make a conclusion. Recall that the null is equivalent to saying that the two population proportions equal to each other. That difference in the population is 0. That's the null hypothesis. Nothing's going on. But we reject the null of no difference between men and women in their views of Wall Street, the alpha of 0.05 level. Specifically, the data seem to suggest that a higher proportion of women than men view Wall Street executives as dishonest. We also want to calculate a confidence interval. Confidence interval is our point estimate for that difference in population proportions plus or minus the margin of error. Using p hat 1 and p hat 2 as point estimates for p1 and p2 when we calculate the standard error, we obtain a 95% confidence interval of 0.065 to 0.195. That confidence interval, that 95% confidence interval, is centered away from 0. This suggests that we can reject the null of no difference between men and women in terms of their proportion, because that confidence interval is centered away from 0. If the null is out, then it's in doubt. And in this case, the null is not included. So we reject the null of no difference at the alpha 0.05 level. Equivalently, the data suggests that a higher proportion of women than men think Wall Street executives are dishonest. So several things to know when we're looking at the difference of two proportions. Right? We can use the two independent sample z-test. This can be used when the sampling distribution of the difference in proportions is approximately normal. This occurs when the expected number of successes and failures for each group is at least 5. We can use the data at hand to assess or check this condition. Intuitively, most of the time, this is just a reflection of the sample size. A larger sample size, we can be more confident that that sampling distribution for that difference of proportions in the sample, that distribution will be approximately normal, and we can use a standard normal model to model that sampling distribution. The null for the difference of two proportions test is that that difference in the population is 0. While in the two-sided test, the alternative is that the difference is not 0. That's by far the most common setup, and it's a difference we will examine and use in this course. With that, we've concluded our discussion of comparing two proportions from two independent samples and using the Z-test for that kind of hypothesis test.